All right, as we talk about bioenergetics and all metabolism, we keep on seeing that water plays a very important role because it's hydrating the molecules, hydrating the ATP. That's going to increase entropy. That's going to do so many things. You're going to allow substances to come together. And we also are seeing that these hydrogen ions are playing often an active role in the enzyme catalysis, in some of the reactions, and also contributing like to fatigue, for example. But I know a lot of people wonder, well, what exactly is this hydrogen ion? Where does it come from? And so I just want to do some basic chemistry on what that is. So let's start with what we call water. Okay, so here we go. We have the water molecule, and it turns out this water molecule self-ionizes all the time, and it does it following this reaction: H plus OH minus. This happens all the time, and this is so it's called the autoprotolysis of water, or the self-ionization of water. Why does that happen? Well, it happens because of this reaction. Okay, you have a water molecule, and let's say you have another water molecule right here. Now, these water molecules are going to be somewhat attracted to each other because first, let's look at this water molecule and notice how it has this bond angle, right? So this is like 104.45 degree angle, right? Why does that happen? It's because there's electrons that are doing electron repulsion. These electrons right here, so the electrons here, and the electrons here, and now you get 8 electrons to form the octet rule, right? So there's 2 electrons, so 2, 4, 6, 8. It's going to be 8 electrons. Now it's a complete, all the valence electrons on the outside orbital of the oxygen are complete. It's a neutral molecule, and it's polar because you can see it's bent at 104.5 degrees. Now the oxygen is slightly, because it's electronegative, it's pulling all those electrons towards it, and so this oxygen molecule has a slight negative charge. Well, that if it's pulling the oxygens away from the hydrogen, then the hydrogen is going to have what? A slight positive charge, right? And then the same thing is also true for over here, right? Where the hydrogens over here are going to be slightly positive, and the electrons here are going to be slightly negative. Well, this oxygen is going to be slightly negative. And this is going to form an association, an attraction between these, right? The slightly positive here is going to be attracted over here, right? There's going to be this attraction. Well, what can happen is these electrons really can grab onto this, and then these electrons are going to just stay over here, and it's going to disassociate the water molecule, okay? It's going to ionize the water molecule. So we can rewrite that. Let's rewrite this exact same molecule here without that hydrogen. So here's the bottom hydrogen right there. This one, there's no more hydrogen, but it does have all these electrons, okay? Now, this is going to have a negative charge because it's not balanced by having that hydrogen ion, which is a proton. The hydrogen ion, by definition, it's a proton, right? And with hydrogen, you just have a proton and an electron. That's all a hydrogen atom is. Take away the electron, which we just did, and now it's just this bare proton. Well, now let's redraw this molecule with that extra hydrogen ion or proton. So here's your oxygen. Here's that hydrogen there. Now let's draw this one right there. Now we'll draw this one. Now it's connected to it in a covalent bond right there. And now it's going to have a positive charge because it was neutral, and now it adds another hydrogen ion to it. So this is the real reaction that's happening all the time. So this is not technically correct. The hydrogen ion alone doesn't really ever exist. Just the proton doesn't exist. So really, we should write this equation as this. So 2 water molecules, okay, see, 1, 2, is going to go through this reversible reaction, and it's going to form what? The H3O ion plus OH minus, all right? And this molecule here is called the hydronium ion, all right? Hydronium ion, it's again, hydrogen ion alone, it doesn't exist into water. Now, the question is, how often does this happen? Like, how do you know this happens, and how much does it happen, and so on? Well, we can measure it. It's really quite simple, and it's very, very sensitive. And we just have to write the K of equilibrium for this reaction, okay? So if we take, this is going to be the K of equilibrium, the constant, okay? Or we can call it the ionic product of water. The ionic product of water. That's the Kw. And we can just write your typical reaction quotient, all right? So you'll have your, remember it's products over reactants. So you have over here are your products. Okay, so H3O plus and OH minus over H2O. And these are going to be the A I wrote as your activities. This is how it is defined, all right? This is the activity of the hydronium ion, activity of the water, activity of this, and this is how the Kw is actually defined. Now, we can sort of simplify this, and instead of doing the activities, we can just do the concentrations, because in pure like dilute water, it's pretty much the same thing. And so instead of doing the activity, let's just do this. We'll just write the, okay, well, maybe I'll just rewrite it actually. So we'll leave A. We'll go like this. We'll go Kw is going to be basically equal to your H3O plus concentration times your OH minus concentration. And the water is not included because when it comes to the reaction equilibria, you don't include liquids or gases like this in their state. So actually, you can include gas. It depends on the situation, but we don't include the water. And so here we have this reactant equilibrium, right? This is our typical equation, and the brackets mean concentration of each. And that means we can measure each of these concentrations, and this would be in molarity, right? And if you did put this into molar concentrations, they actually cancel out. Again, if we had water here, you'd have moles times moles is moles squared, and then water moles squared is moles squared because it's raised to the 2, right? The 2 coefficient. And so the moles cancel out. So the Kw number is dimensionless. It's unity. All right, I just want to clarify why these constants are often don't have the values with it, right? Why is it they don't have their actual units? And that's because it's unity. It's a dimensionless state. That's how it is in their standard form. Okay, so now we have HCO and OH minus. That's the ionic product. It's called product, right? Because you're multiplying these together. And when you do that, you get this number, which is 1 times 10 to the negative 14. All right? That means that if you multiply this together, because it's the product, multiply the concentrations, the molar concentrations, you would get 1 times 10 to the negative 14. That's a constant. That you always get that. It doesn't matter how much of this or this one you have, they just change according to this equation, so you will get 1 times 10 to the negative 14. That is why it's called a constant, and it's the ionic product of water. Now, if that's true, then that means that for every hydronium molecule you get 1 molecule of hydroxide, because it's a 1-to-1 ratio, right? See right here? You created 1 hydronium ion, therefore you created what? 1 hydroxide ion, so 1-to-1 ratio. So this right here, you can see that if you divided this number precisely, by 2, you would find that basically your hydronium ion, actually I don't want to confuse you with this. Your hydronium ion concentration is going to equal to what? 1 times 10 to the negative 7 molar. Okay? That's what your hydronium ion concentration has to equal to. And the hydroxide concentration would also have to be equal to that. So again, you take pure water, and it's a pH 7. It is pH 7, and the question is, why is it at pH 7? And this is the reason why, because it's the ionic product of water. You don't have anything in the water. There are no minerals. There's nothing that's happening. There's a 104.45 bond angle. And when you do all of that, then this process happens at exactly this constant, 1 times 10 to the negative 14. Now let's go to the pH aspect. What does that mean? Okay, so if we go pH, all right, well, the question is, what does that mean? Well, the P stands for power or potential, and specifically the power of 10, but it's the power potential in an inverse way. So it's an exponent, but it's the inverse exponent. And it also is as a negative inverse exponent, which is a log. So technically, it is the negative log. All right, that is what P means. The H has reference to what? What does the H mean? The H has reference to the hydrogen ion concentration. Okay, here, the hydrogen ion concentration. In other words, the hydronium ion concentration. That's what the definition of pH means, is simply, what is the concentration of hydronium ion? Well, we can now calculate what the pH is in pure water, right? Because we know what the Kw is. We know this constant right here, we know what the Kw is. It's 1 times 10 to the negative 14, okay? And therefore, we know that the hydronium ion concentration in moles is 1 times 10 to the negative 7. So let's do this. Okay, negative log of 1 times 10 to the negative 7. And because it's a log, right, you just move that number and you get negative 7. And negative 7 times the negative 1, so for a log, is going to give you what? 7, right? 7. So therefore, 7 is what the pH is. So that means that neutral water has a pH of 7. That's how we know that neutral water is a pH of 7, precisely because we know what the ionic product of water is. It's 1 times 10 to the negative 14. Now, this also illustrates a number of very important things that I'm going to get to. Number one, very small changes in the hydrogen ion concentration, we can detect that. Look at this. This is 1 times 10 to the negative 7 moles. The pH scale goes from 0 to 14. That means that at a pH of 14, we would have 1 times 10 to the negative 14 moles of the hydrogen ion. And that is order of the magnitude. I mean, that's negative 14. That's going 0.000000, right, all the way to negative 14 moles compared to, let's say, the concentration of water, which is about 55.5 moles, molar concentration of water, if we looked at the concentration of water, right? Now, why is this important? Because in the body, our pH is tightly regulated, right? We need to have a pH of around 7.35, 7.45, and then of course the cells themselves, muscle cells, going down to pH 6.5, maybe a little bit lower. And then the matrix of the mitochondria, for example, can be a pH closer to 8 even. These pH gradients, really it's about the hydrogen ion gradients. These hydrogen ion gradients are critical for your sodium potassium ATPase pumps. They're involved in fatigue. They're involved in the enzyme catalysis as a specific acid-base chemistry or in general acid-base chemistry. This is so important. And there's another aspect that I want to touch on, because these days there's a lot of claims about so-called structured water, and you can, or changing the hydrogen bond angle and things. And this simple high school level definition of pH actually totally eradicates those claims completely. And that's because, as I said, we know that the ionic product is 1 times 10 to the negative 14. Meaning if you just take water, it always is doing this. And if you just change this ionization just a little bit, then you will change the ionic product of water. If you change the ionic product of water, you will change the hydrogen ion concentration. And for example, if you took, say, a little bit of some minerals, just a little bit of salt, for example, if you did that, guess what would happen? When you put salt or things into the water, you'll take that water molecule and you cause the hydration spheres around those ions. And therefore, you start changing this constant. Now the Kw has changed. Because the Kw has changed, the pH has changed. So by adding minerals and salts or anything to the water, you slightly change the pH. You slightly change the hydrogen ion concentration. Why? Because you change the Kw, you change the ionic product of water. If you were to heat the water up a little bit, because this is at 25 degrees Celsius, okay? This is at 25 degrees Celsius. If you were to measure the pH at, say, 37 degrees Celsius, right? 50 degrees Celsius, any temperature, a colder temperature, what happens? Well, if it's a colder temperature, then this is going to happen less often, right? There's less thermal energy for this to occur. If there's less thermal energy for this to occur, then the Kw is going to also change, right? It's not going to be quite as high. Therefore, the hydrogen ion concentration is not going to be quite as high. If you use a different isotope, so instead of the hydrogen ion, you use deuterium ion, right, which has another neutron. If you use that, then the pH would also be different. So the pH is extremely sensitive to the smallest changes in water. Whatever changed the ionic part of water would change the pH because of this very relationship. If you change the hydrogen bond angle just a little bit, right? This is 104.45. You change this just a little bit for whatever magical way you're doing it, then you're going to change this reaction. You're going to change this, and therefore you're going to do what? You're going to change the ionic part of water. You change the ionic part of water, you're going to change the hydronium ion concentration. By doing that, you're going to change the pH. And again, think about how sensitive this is. You can go up to 1 × 10⁻14 moles. That's 0.0000 up to 14 zeros compared to water at 55.5 millimolar. So therefore, any minor changes, whether it's magnets or some energy or putting some sort of frequencies or anything into water at all, is going to change the ionic product of water. And therefore, it's going to change what the hydronium ion concentration is. And therefore, it's going to change the pH. And you can simply measure the pH to see if there's any change. And when you do under the controlled laboratory grade studies, and you take into consideration different fluctuations and things, you'll see there's no change. Because actually, to really measure the concentration correctly, you don't necessarily use a pH meter, because when you do that, you're actually measuring the activity of the hydrogen ion, not necessarily the concentration. And so we go into a whole other analytical field of measuring temperature or pH changes. So I also don't want you to think, oh, look, I put the pH probe in, and therefore we changed the pH was changed a little bit, therefore all this changed. No, that's not necessarily what it means. We need more sophisticated laboratory equipment, because we actually want to measure the hydrogen ion activity. That's why I wrote the activity of the hydrogen ion concentration. That's really what we want to measure. And the other neat thing about knowing the Kw is it'll tell you how much energy that water has, because we have our equation of delta G is equal to negative RT times the ln of K, in this case, K of Kw, right? Right here, right there. So if you change the Kw just a little bit, which is very sensitive, okay, then you're going to change this equation. And you take the ln, the natural log of that, multiply by the temperature and the gas constant, you're going to be able to tell you what the free energy change is. What is the actual energy of the system? So if people are saying, look, we put this energy into water or something, well, then we should easily be able to measure those changes, and we can do so by looking at simply the pH, the hydrogen ion concentration. Well, not actually the concentration, but looking at the activity of the hydrogen ion. And when that's done over and over again, there's no difference, unless you're adding solutes, right? You're adding ions and minerals, you're changing the temperature, and you're changing all these other variables, because we know that those things directly change all of these dynamics, and therefore you end up changing the Kw of water and change everything else. So going back to bioenergetics and biology, this is very important to understand because of the importance of the hydrogen ion in metabolism and in the cells and in physiology, everything because of that importance of pH. In fact, it is that hydrogen ion, the hydronium ion, that goes through the ATP synthase enzyme and drives that little nanomotor to create ATP. So this is so important, and it all comes from our lovely water molecule. So this is involved in pretty much all of our biochemical reactions in the body.